Hello, my name is Mel Friedman. This work was done in collaboration with Dr. Brian Mark, a professor at George Mason University. What I'm going to talk about today is how can you coordinate traffic signals on existing two-way roads? I have provided some references for you. You probably look at these when you can see the recording. One is a video which has some of the material presented here. And the second reference is a one-page description of an invention application that describes the work that describes this work. I'll start with some definitions and notation. Blocks are the gray squares in the demonstration, and here's the demonstration. Green waves are represented by these arrows which are heading in two directions on a perfectly rectangular network of roads. The RGW roads are these white spaces between the gray squares. RGW roads are the roads where motorists who travel at a recommended speed make all traffic signals. One way to think of this is that these green waves or green arrows keep moving forever without ever stopping. And you can think of them as actually controlling the traffic light. So a traffic light is only green in the direction of the green arrow, while a green arrow is going through the intersection. The other thing that I could say is that with this system, like in a highway system, motorists who go at the speed of the green arrows make every traffic light. So it's like they're on a little highway. And the capacity of these individual arterial roads is a little less than half that of a highway lane. That is, each lane on an arterial road has an ability to carry a number of cars per hour, roughly half that of a highway lane. And the reason it's roughly half is because in the animation, the green arrows only cover half of the space. A very important concept is that of nodes, and that's the location where RGW roads intersect one another. So for example, where my pointer is now is a node. There's some elementary notation that you need to kind of be familiar with. TG is the time a traffic light is green in any given direction. And the travel signal cycle time is the amount of time for a traffic signal sequence to repeat the cycle. And since the cycle consists of a light being green for time TG in this direction, and then it's green for time TG in this direction, so the total cycle time is 2TG. And we use the notation VG for the speed of the green waves. And here are some perspectives that will help you think about it. Green waves, which never stop moving, turn traffic signals on and off when they enter and leave intersections. Another way to look at it is green waves traveling with a speed VG are emitted whenever traffic lights turn on. So this interpretation is really good for seeing that the cars will be able to make all the traffic lights. But since the green lights turn on and off periodically, this is a good interpretation when you're trying to actually build the system. There are some observations one can make looking at this demonstration. Each green arrow is a distance between nodes. So here's like one node, and here's another node, and the green arrow is very nearly equal to that distance. The other thing that you want to realize is that the system works regardless of the network size or the green arrow speed. And I can demonstrate that. First, we'll demonstrate that it works regardless of the size. Here I've increased the size enormously. And when you look at this video, you see that the green arrows never stop moving. And since they represent platoons of vehicles, they also never intersect each other. Because if the green arrows were to intersect one another, that would indicate platoons of vehicles would be crashing into each other. So I've shown that it works regardless of size. And now I'll go back to a more convenient size to visualize things. And I'll show that it works regardless of speed. So I just slowed it down. And I guess you'd have to wait a long time to see that it's going to work. So what I'll do is I'll speed it up. And you'll see that it works regardless of the speed. And it works regardless of, now I'll slow it down again. And it works regardless of the size of the city. So that means, what this means, it'll work in any city. That is, any city that has a perfectly rectangular grid like this. Now, there's another important observation that helps you actually implement this. You'll notice that these two green arrows enter an intersection at the same time. And if you look at it for another cycle, at any other point, like we go over here, two green arrows are entering an intersection at the same time. And so essentially, that means that at the nodes, one can coordinate the traffic lights by simply following a green arrow in one direction. And so that means it's rather easy to coordinate the traffic signals at nodes. Another thing I would like you to realize, looking at this video, is that each intersection is fully utilized, so that a green arrow is always going through the intersection, either in the north-south or the east-west direction. And you've just seen that, and that's true regardless of what intersection you're looking at. And so the fact that a green arrow is always going through an intersection means that the system has the maximum flow possible. That's really nice that you have the maximum flow, because that means you have the maximum capacity to carry vehicles. But there's a price paid for maximum flow. There's no time, the way this is currently configured, for a vehicle to make a left turn onto another street. And I'll show you how that is addressed using left turnarounds shortly on this slide. However, if you don't need the maximum flow, so off of peak flow, you can make direct left turns the way you normally would. I'm going to skip some mathematical details. I'll show you what a cloverleaf left turn looks like. Here's what a cloverleaf left turn looks like on a highway. You go like this, you come around like this, and so this vehicle that was heading north is essentially turned left using the cloverleaf. In the city, the way that works is these black lines are actually side streets. And here's an RGW road where you make all the traffic signals. Here's another RGW road where you make all the traffic signals. So the usual way of making a left turn, I call a direct left turn, is indicated by this dotted arrow. So you go up here and you make a left turn, and actually simultaneously a fellow heading south can also make a left turn. Now, if you have the maximum flow as illustrated here, so you really can't make a left turn like this because that would interrupt the flow heading in the southern direction. So the way you do it, the way you make a left turn is you go here, you go past the intersection where you want to make the left turn, and then you make 3 right turns. Here's one right turn, here's a second right turn, and here's a third right turn. So 3 right turns are equivalent to a left turn. And so I described Cloverleaf and direct left turn method. And there is something called the left turn arrow. So that these arrows move the same way as these arrows here. But if a vehicle is in this blue portion of the arrow, then that vehicles in here can make a left turn going this way, and vehicles going this way can make a left turn this way. So left turn arrows allow people to make left turns when you don't need the maximum flow. And now I'm about to say the problem that's going to be solved in this presentation. We know from this video, which is for an ideal system of roads, that each intersection is fully utilized and the result is uninterrupted maximum flow. The object of the work that I'm going to describe to you today is to extend this result to existing roads and road networks. And essentially what I'm going to do is I'm going to show you a method that turns existing arterial roads into essentially low-speed highways with vehicles traveling at the recommended speed, make all traffic signals, and have maximum flow. The thing that I'm going to do is not going to be quite as good as turning it into highways, because on these roads you'll travel at a lower speed than highways, but it will have roughly half the capacity of a highway. Each lane over here in the work that I'm going to describe will have roughly half the capacity of a highway lane for carrying traffic. And now as we go into trying to explain how we're going to extend this work to an existing road network, here's a static depiction of the scene that you're seeing here, only it's covering even less space than that shown here. And here is a real network that's a real road network that's topologically equivalent to this one on the left, which is ideal. So for example, here's a 0.11 and there's a corresponding point here. Essentially, this thing on the right is just a distortion of the image I'm showing you on the right. So, this is a distorted image of this scene here, which is on the left. So here's the intersection 1, 2, and the intersection 1, 2, and 1, 3, and 1, 3, and 2, 2, and 2, 2. So every point here, every node here has a corresponding node here. Now here, as you see in this diagram, the arrows, the green arrows are moving at a constant speed. And what we want to do is we want to map the motion that's taking place here, or that's taking place here, onto the corresponding motion here. And the way we can do that is if this road segment is, let's say, k times bigger, longer than this road segment, we just have the green arrows move with a speed k greater than it was here. If it moves with a speed k greater and it's k greater, a k distance further away, then a green arrow that starts out here and starts out here will arrive here at the same time as the green arrow arrives here. So basically, the traffic lights at these nodes turn on and off exactly in sync with the traffic signals on these nodes. And the only difference is that here, green arrows move at a constant speed, and here, green arrows move at a speed that's proportional to the ratio of this length to this length. And so the things I want you to take away from here is that the green arrows in both the ideal and the real system turn on and off simultaneously. In this situation, the green arrows move at constant speed. In this one, they move at a variable speed that depends on the size of the distance between nodes. And essentially, there's a mapping of if you looked at this picture, you would understand exactly how green arrows were moving in this picture. And with that, I'll go on to the next slide. Now, what I'm going to do as a starter is I'm only going to coordinate roads on a single road. And it's going to happen to be a road that runs north and south. But you see, an arbitrary road that runs north and south could be this one, like 1, 3, going to 2, 3, going to 3, 3, going to 4, 3. So this could be an arbitrary road heading north or south. And using this notion that if I just multiply the speed of the vehicle by the ratio, this ratio to this ratio of lengths, then the traffic lights will turn on and off automatically. And it'll work equally with horizontal, with north-south streets or east-west streets. And so that's what I wanted to communicate here. Now, there is a problem with what I showed in the previous slide. And the problem is, if the distance between nodes is really great, then the green waves may be moving quicker than the speed limit. And so there's a way to counter that. You can introduce phantom nodes. And with phantom nodes are there nodes that are placed. I'll go back to the previous view graph. For example, here, if a vehicle went from here to here, and this was a reasonable speed at the at this corner, then the speed over here might be really excessive, might be above the speed limit. That is, the greenways might be going too quickly. But suppose I put in just a node over here, or in this case, it would be like a node over here, so that wouldn't be such a great distance. Oh, no, I'm sorry. I guess that's corresponding to this point. Corresponding to this point. So essentially, you put in nodes to slow down the green waves because otherwise the green waves will go too fast for the vehicles to keep up with, or either that or they'll violate the speed limit. So since the green waves move at a variable speed, and the objective is to have vehicles moving with the green wave, you need a way to let vehicles know where they are relative to a green wave and how fast the green waves are going. And this diagram illustrates that. This rectangle here, or this rectangle indicates the location of your vehicle. The road to traveler feedback device is a smartphone device that would be installed in vehicles, and it would show where green waves are and where your vehicle is relative to a green wave. So this says that you're 1/10 of a mile away from this green wave, and that there's a green wave behind you, but it's 9/10 of a mile away. It also tells you that this green wave is moving at 35 miles per hour, but the green wave behind you is moving at 30 miles per hour. It tells you your vehicle's speed is 38 miles per hour, so that if you just keep going at your regular speed, you'll enter this green wave. And then if you stay in this green wave, as illustrated here, then you'll make every traffic light as long as you stay there. This red line over here tells you you're traveling during peak flow, so that you're not allowed to make a direct left turn. But on your smartphone, it also tells you where there are left turnarounds. So here's the left turnaround for you. And then if you're off peak flow, there's a blue section which says if you're in this blue section of the arrow, then when you come to an intersection, you'll be able to make a left turn without stopping. And it also gives you some feedback as to when pedestrians can cross. And that's indicated by these three dots throughout the diagram. So when this green arrow is in this intersection, and during that period, pedestrians will be able to cross the street going this way or going this way. So now I'm going to show you where we coordinated the traffic lights. I did it on an existing road. It's called Telegraph Road, and it starts here, and it's also called 611, and it ends, or I synchronized it up to the place where it intersects this road here. So just shy of the Beltway, which is 495. Now, to do this work, I needed to know the distance between traffic signals. And one way to do that is to just drive around in your car and locate traffic signals on a map, and then find out with your car odometer how far away traffic signals are from one another. But there's a much better way to do it, and that's with Google Map. So on Telegraph Road, I started here on Richmond Highway, which is Route 1, and the first traffic signal is indicated on Google Map. If you zoom up to a really high level, there's a traffic signal here and a traffic signal here. And on Google Map, by doing suitable operations, you can find out what the distance is along this black curve that I've shown. And it shows here that that distance is actually 523.7 feet. So here you're measuring the distance between intersections to within a fraction of a foot. And that's far, far better than trying to do it with your car odometer, which is what I tried first. And now I can tell you what the results are. So there on this table, there are some things that you really want to pay attention to. This is the speed that you should be traveling at when you go between Belvoir Woods Parkway. Actually, I'll make this bigger. So this says you should, when you're traveling from Route 1 to Belvoir Woods Parkway, you should be traveling at 39.6 miles per hour to make the traffic light. And when you're going between this street, or let's do Lockport Place, to Fairfax County, you should be going at about 30 miles per hour. This symbol here tells you how long the traffic light will be green in the Telegraph Road direction. This one here tells you how long the traffic light is green in the direction perpendicular to a Telegraph Road. And this tells you when these traffic lights along Telegraph Road turn green. So what this means is that, now there's another thing I should point out. Yellow highlighting means that you're at a node. So sometimes there are phantom nodes, and sometimes there are real nodes. Like here's Route 1 is a real node, and Newington is a real node. And real nodes are highlighted in yellow. That actually facilitates the calculation and facilitates the interpretation of the calculation. Now, so because the and what this column over here does is it has followed the motion of a green arrow starting off at Route 1 and going the whole length of the road to Huntington Avenue. And actually it goes a little bit past Huntington Avenue to a location at 11.15 miles along Telegraph Road away from Route 1. And there's an interesting thing that you can observe here, which shows that this is reasonable. It takes a time, TG, to go from one node to another. So this time has gone from 0 to 60, and then it takes 60 seconds to go from this node to this node. But since we're putting this in a cycle time, so that's indicated here by 120 seconds. But this column are the values over here, mod 120. So 120 mod 120 has a 0 remainder. So this goes, as you would expect, 0, 60, 0, 60, 0, 60, 0, 60. And these offset times were calculated. Oh, well, I'll tell that I'm almost out of time. First, let me explain how you use this table. So, for example, at 60 seconds into a cycle, the green light on Telegraph Road turns green for 60 seconds. Then for another 60 seconds, it's green in the orthogonal direction. And that brings you back to this, back to 60 seconds again. So that this tells you essentially when this green light turns on, and also this tells you, this number tells you when this green light turns on. This value in here tells you how long that green light is on. And then this tells you when this green light turns off, this green light turns on. And I've done that for every intersection on Route 1, on Telegraph Road. Now, the hard part of this calculation is actually routine. That is, it can all be done by your computer once you decide where the nodes are. And the way I found out where the nodes are by making a graph like this. So these blue dots represent existing traffic lights on Telegraph Road. And then places where I've decided to place nodes are these tan dots. And over here is a scale that gives the mileage to the nearest 10th along the road. This over here shows a graph of the speed you should go at to make every traffic light on Telegraph Road. The nominal speed limit on Telegraph Road is 35 miles per hour. In that graph that I just showed you, this shows the speed you should go. This red curve shows the speed you should go with a cycle time of 120 seconds. And you see the speeds are reasonable in the sense you're not really going too slow. You're going a little bit above the speed limit and sometimes a little bit below the speed limit. However, if a traffic engineer felt that this maximum speed limit was too high, they could just increase the cycle time from 120 seconds to 150 seconds, and then the proper speed for a vehicle to make every traffic light would be indicated by this black line. And so you can speed the traffic up or you can slow it down to accommodate your goals. At rush hour, you would probably want to slow it down, and you can slow it down even further if you made the cycle time a little longer. I don't have time for this now, but this is the method that I use to figure out what the offset times were. And now I'll conclude my talk and take your questions. First, I'll just say the main result. What I've done is I found a method for coordinating traffic signals on suburban arterial roads such that the motorists who go with the recommended speed make every traffic signal. And this is a mathematical result. So if the mathematics is correct, the result is correct. I've checked the mathematics and I believe the result is valid. And because the green arrows move with a speed that depends on position on the road, you need a feedback device to tell you what speed you should go. Finally, I would like to say mathematics, graphics, and animation capability greatly facilitated this work. I probably wouldn't have tried it without Mathematica. I have coordinated traffic signals on a suburban road. It's not clear that this technique would work on urban roads. Although I haven't described it here, I have also coordinated traffic lights on a network of 3 east-west roads and 4 north-south roads in the vicinity of George Mason University, so that vehicles going at the recommended speed on those roads would make every traffic light. And in closing, I would like to thank you for attending this presentation. And it has been my pleasure to share these results with you. And now I'll take your questions.
Okay, you have time for a couple quick questions, Melvin.
Yes.
Thomas has asked, mid-block traffic emanators or sponges, railroad interactions and grade separated highways are problematic for our community. Any suggestions on adding those to your model?
Well, crossroad traffic has already been accommodated. The times at non-nodes were actually for cross traffic. In terms of a train going by, if I knew the train schedule, I might be able to adjust the green wave speed so that the green waves would accommodate the train crossing the track. It's not, I haven't really done that yet, so I don't know if that's possible.
And then Benny also asked, how did you determine the, I'm not sure the annotation, but if you scroll down a little bit on your page, you'll see it, but the T_G for a traffic light on an actual road?
Well, the way I did it is I picked, the way I did it is the roads that I was considering had a speed limit. And what I did is I try to make the speed limit multiplied by TG to be roughly equal to the distance between traffic signals. And so that's what determined the first guess for TG. TG, of course, could be changed up or down. When I did the analysis on Telegraph Road, I started with 1 minute, and that was actually, there was another consideration that caused a 1 minute for the length of TG, which is actually also determining the cycle time. There's a highway that has 2 exits that come out to Telegraph Road, and those 2 exits are close together. So if I made TG too long, then it's possible the traffic would back up so much at those traffic signals that that we would have something called overflow, which is not a good thing to have. So I don't think, so basically I have told you two considerations for selecting a TG. One is it was actually determined to be as long as possible because if it's as long as possible without causing problems, then you have less time clearing traffic when you have a yellow, that is clearing intersections. And the other consideration was I didn't want there to be overflow at certain intersections.
Yep, and I think that also touches on the next question of what happens during rush hour.
Well, during rush hour, what you would do is you would increase the cycle time. By increasing the cycle time, as shown in one of the last graphics that I showed, I can slow the green wave to whatever speed I like. I could also actually put nodes in different places and actually have a traffic engineer just switch the coordination from one green wave speed to another green wave speed by suitably placing nodes and by redesigning the traffic system so that I could decrease the green wave speed either by, the easy way to do it is by increasing the cycle time. Another way to do it is by having another design that allows vehicles to make every traffic light, but traveling at a slower speed.
Okay, and that looks like that was all the questions, and we're also pushing very close to the 10-minute over mark, so.
Okay, well, thank you all so much for listening. It was my pleasure to answer your questions and to present my material with you.